Okay, thank you for rejoining. So, hello. If there is any
Yes,
question,
ma'am. No
can you
question, ma'am.
Okay, thank you. So, up till now, we have taken the three main topics, which were the ring closing metathesis. We have talked about the asymmetric metathesis, closed metathesis, and third, we have taken the tandem metathesis. Now, we will move to the very important topic, which is your another part of ring closing metathesis, but it involves ring opening as well as ring closing. So the name is ring opening, ring closing, metathesis reaction. So this is RORCM, or it is known as ring rearrangement metathesis. So in our previous session, we have seen how the ring which is closed, it gets opened up. That is that comes under the metathesis. Similarly, we have seen if if two alkenes are there, how they close and to form a new ring. So here both the processes would be happening. First, one ring which is closed, that would be opening, and then the two alkenes which are there, they would close together to form a more stable product. So firstly, we will take up this example where we have a chiral moiety. This is having a five-membered ring which is closed with a group acetate, this acetate, and here we are having this acetate. Okay. So as I said, when we need to have a metathesis reaction, so firstly, this can't undergo metathesis with any other alkene because it is not having other alkene present. What we can do, firstly, this alkene, which is closed over here, we will break it, we will open it. So first step would be ring opening metathesis. So how this ring could be opened, if you will see, it's a combination of CH2 and CH2. So this is having nothing but the CH2 and CH2. So this would just be having this kind of moiety. You have to make sure that these are having alkene. If you will try to make again this closing, these two would combine to form a double bond and their CH2 would be leaving as another group. So this is your ring opening metathesis. The other groups remain as it is. And I hope this is clear. We have done nothing. I'll just explain it one more time. What we are actually doing. If I am having this product, if I'm having this substrate, which is having these two acyclic alkenes. So one part is this one, other is this one. I'm just highlighting it with dots, which have to be combined. And this part, star parts, they have to combine to give one alkene that is called as metathesis. So here, if we will just see the product, this and this would combine to give you alkene. These are the dot products. This has closed the ring, and the other star one is nothing but the CH2CH2. This is your ethylene. So this is your ring closing mechanism. But if I have this product, if I have this is as my substrate, then what do you expect it to come from? So it would, if it goes reverse process, ring opening metathesis, then it would tend to give you this kind of substrate. I hope this is clear. This is the same thing that we have tried over here. Here we were combining the two to give us the product. Now this is our substrate over here. This is a cyclic substrate. And now we are opening it and to give you this kind of product. So this is ring opening. If I'll just do the ring closing, it would give me again this one. But in presence of this other alkene, now the competition will start, which is going to again either it is going to give me this 5-membered ring again, or these two alkenes could combine together to give me a different product. So since this part would not happen, because if you will see over here, one, two, sorry, one, two, three, and this one 4, 5, and 6. Now this is going to form a 6-membered ring, where if it will recombine with this one, it would form a 5-membered ring, and 6-membered ring is more stable compared to the 5-membered ring. That's where this particular product would become a major product, and this is the driving force for having this kind of ring opening, ring closing metathesis. I'll just repeat it one more time. So now after the first ring opening metathesis, the product so we have obtained is nothing but this one. This is the wedge sign which shows the out of above the plane, and here we have double bonded CH2. Here we are having O acetate, O acetate. Don't worry about these groups. So what we will do now, it will undergo the ring closing metathesis. This is 1, 2, 3, 4, 5, and 6. The star mark they would leave as CH2, double bond CH2. So if you will try to combine this, I will firstly make a 6-membered ring, because I know it is going to form a 6-membered ring. Now just name it 1, 6, 5, 4, 3, 2. Now which two carbons are going to give you the compound? This 4 and 5 is going to give you a double bond over here, and the rest parts would remain as it is. Third carbon was having O acetate group, form an O acetate group over here. Similarly, your 2 carbon was having this kind of groups, which is O acetate and double bonded A, and nitrogen was having acetate. So this is the way we are going to form your reaction product. So this is the 6-membered ring that is going to be formed. And since 6-membered ring is more stable, so this is your product and it is not going back to combine with this one. I hope this is clear to all of you that how we are coming to the product formation and why it is not going again back to the same product which has been opened. So the 5-membered ring is less stable comparative to 6-membered ring. So as soon as the alkene is getting chance to make a 6-membered ring with this one, it would just combine and form a 6-membered ring, and the other part remains as it is. Okay, so this is the one such example, very important example of ring opening, ring closing metathesis. Now another example which is again very important, we are going to take of NOR-boron kind of system. So you have already seen in previous lectures how this NOR-boron kind of systems they try to go undergo ring opening because of the strain in the ring. So this is a 7-membered ring where 7 carbon is bridged one, and now we have this kind of alkene which wants to combine with this one. But firstly, it will undergo the ring opening metathesis because of the ring strain. And how it is going to form? Again, the same process. Since this C and C are combined, we can expect it to have. So I'm just highlighting here. So you just have to follow the process. It looked very complicated, but it is not. So you keep everything as it is and try to just see how the groups are coming and being formed, because this could also be a question can be asked in your exam, where how this particular ring has been formed. If you will carefully see over here, if I'll just be having these dot products undergo the metathesis, they would be having the double bond as it is, and the side product would be the star and star CH2 would combine together to give you the ethylene. So this is your ring opening metathesis step, step number 1. Now, if you will see here, we have two types of alkenes which are more or less same because it's a five-member ring and both are having the same group. So if either this combines or this combines, so that is not a problem. Now again, the possibility of combination of these two, why? Because the number has been increased. If I'll just name it over here, if this is your this part, okay, we have one, two, three, four. This will combine with your this is five, this is your six. So this will again form a six-member ring. How? We will just take a look of it. So what I said, it was having so I said one, two, three, four, and this is your five, this is your six, this is A, B, C. So firstly, this one A, B, C combination, we will just form a five-member ring, which is one over here, five here. This is A, B, C, and this five is going to combine with your six. Six is going to combine with your four, four, then with three, which is having double bonded O, which is with two, and then with one. I hope this is clear. It looks a bit complicated, but if you just name it, you won't be making any mistake in forming the product. You just have to name it according to your wish. It is not mandatory that you have to follow some nomenclature or some trend. You can form it as it is. So this is your two. So you can just again see why we have made the five-member ring first, because it is easy to form the six-member ring. So this is your six-member ring. One, one, two, three, four. The four, one, two, three, four is forming this one. Now this four has to combine with the six. That's why we form the six over here, which is already connected with the five, and five is connected with the one. So this ring is being closed, which is a six-member ring. And already we were having this one A, B, C, five and a five-member ring. Now just put the substituents wherever it is. A was having this double bonded alkene. Five, six is there, and 3 is already been given. So the side product would be your this CH2 and this CH2, CH3, CH2, double bond CH, CH3. If you will just see, this is your star marked CH having a group of methyl, and this is star marked CH2, which is the side product. So here it was forming a six-membered ring, and therefore it becomes your product, and it does not go again back to make a bridged seven-membered ring, which is having high strength. I hope this is clear. This is another very important example of ring opening, ring closing metathesis. So with that, we can move ahead to give you another. Now, the last part of our today's discussion, like lecture, before explaining the assignments, is the metathesis, alkyne metathesis. So the name suggests we have already seen that in case of, just to give you a recap, if I am having R1, R2, so this is just a CH2, CH2 group. These carbons, which are dotted, they would form one double bond. Star ones would form another double bond. So the star ones is nothing but CH2, CH2, that is ethylene, and the dotted ones, R1 and R2, this could be E or Z form, anything cis or trans form. So this is your cross metathesis with alkenes. Similar thing happens when we are talking about alkyne. So if I am having a certain example where R1 C triple bond C, R2 R3 C triple bond C, R4. So these two carbons could combine together and these could combine together to give you the product as what we have combined, R2 and R4, R1 and R3. So this is nothing but your alkyne cross metathesis. We have already known metathesis is nothing but cutting and joining the parts. So one side of the alkene or alkyne would cut, this is cut and this is combined with the other part. This has been cut and this is combined with the other part. That comes under the alkyne cross metathesis. One quick example that we can take is if you have, this is the first example of your alkyne metathesis, which has been witnessed by Mortex in 1974. Sometimes these dates are also important to remember. So example was two molecules of this alkyne, which is having different groups. They undergo self-metathesis in presence of molybdenum carbonyl catalyst and resourcing at 160 degrees Celsius, 3 hours of time. So how this works, I'll just write the product first. So it would give you MCCH, C triple bond C, C6H4 Me plus the other product is C6H5, C triple bond C6H5. So this is the second product. How it is happening? Mechanism is very straightforward, where we have C6H5, C triple bond C6H4 Me. Since we are taking two molecules, we'll write the other molecule just beneath it. So these two would combine together and the other one which is highlighted in red, these two would combine together. This comes under self-metathesis reaction. So just write the C triple bond C and the groups would be C6H5, C6H5, and here C triple bond C, the groups would be C6H4Me, C6H4Me. So this is your self metathesis, because self metathesis is nothing but when you are having same types of molecules. So these two are same molecules, that's why it is self metathesis. If we would be having, say for example, C6H5, C triple bond C, C6H4, and the other group would be CH3, C triple bond CCH3. Now this is first alkyne, this is your second alkyne, and when they are combining, that is called as cross metathesis because they are different products, different substrates. So now if this combines with this one, it would give you a different product. This combines with this one, it would give you a different product, right? I hope this is clear. So this is one or two such examples of alkyne metathesis. It is also very important that alkyne metathesis can be seen, important points, that alkyne metathesis can be proceeded symmetrically in both ine and ine and in mixed substrates, which is ene and ine. Ene and ine is when we are having substrates with triple bonds or substrates with double bond and triple bond. There also you will call it as a alkyne metathesis. So I hope this is clear. Now we can see some examples of ring closing metathesis in case of the alkyne system. Ring closing metathesis of alkynes. So this actually works under high dilutions. It can't be under concentrated solutions. It has to be under high dilutions. And this lead to formation of a cycloalkyne. Anyway, we know that we are talking about the ring closing that would give you a cycloalkyne. And a side product would be a volatile open alkyne, which volatile means it could easily be evaporated. So that goes away. So ring closing would lead to a cyclic alkyne and an open alkyne. For example, we have any group which is combined with these two groups. So this could be any chain, and this is an intramolecular ring, intramolecular ring closing metathesis. And here the catalyst that we are using is a tungsten based catalyst, which is your metal carbene. So this is metal carbene. This is your metal carbine. Sorry, not carbine, carbine, because it is having metal triple bond C. So this is your catalyst to carry out the intramolecular ring closing metathesis. So as I said that this group, these marked carbons, these stars and stars will form a triple bond and the other ones will form another triple bond. So if we'll just form it over here, it has to be closed. So this was your star, this was your star, and R1 dotted, sorry, this is R2. So this is nothing but a volatile. Volatile means having a very less boiling point, low boiling point. Volatile alkyne, open alkyne. This is open, this is not a closed one, and this is your closed or cycloalkyne. Is there any doubt? If yes, please let me know. If I'm going anywhere very fast and if you're not able to understand the concept, please let me know so that I can make it more simplified. If up to this point you have understood everything, please give the thumbs up or unmute yourself. Okay, great. Thank you for your response. Now we can go further. Now we can take an example to see how it happens when we are having a both alkyne and alkene system in one system and how the mechanism happens. So we have a very important example. So this is having a double bond here, and this chain is elongated to give you a alkyne. This is having another alkene here and a methyl group. Now, in presence of Grubbs catalyst, first generation, what will happen? Firstly, it will undergo when we have different choice of the catalyst would lead to different products. So when I have given the first step as a first generation catalyst, which is nothing but a metal carbene catalyst, CH. This is ruthenium, and here we have PCY3, PCY3, chlorine and chlorine. So this is your Grubbs first generation catalyst. When we have this system, so in this system, we know this acts as a, this is your metal carbene catalyst, and that would lead to your ene metathesis. So out of the two things, so in presence of your catalyst, it would direct it to combine these two alkenes to give a cyclic product. Again, the internal part would combine to give a one ring. If I will mark it as 1, 2, 3, 4, and 5, this is a 5-member ring. And the star part would be giving you a CH2 and CH2. So now we will form the main product. So we'll just form a 5-member ring where it is having 3, 2 was having methyl. This is 1, which is combined with 5, this 4, and 5 is having a chain of this one. Right? So this is your in metathesis. Now, this in metathesis can undergo now I9 metathesis. How? Because we were having an ion alkyne bond also. So I'm just forming the product. So we just saw in presence of the metal carbine, we just saw one example. So this is your now metal carbine, and now it will try to undergo or do the metathesis of your alkyne. So alkyne, if no other alkyne is there, then it will undergo first the self metathesis. If you don't find any other alkyne with which it can undergo metathesis, that means you have to take 2 units of it. And this 2 units, it will do nothing. It will just extend the ring to this form. So you will be having this group and same group at the other end. This is very simple mechanism which we have already seen. So this is your self metathesis product, and it would all, there won't be any question of E or Z isomer, because E and Z isomer will need to have at least one more product, so which can direct the direction. It would always be in this particular form. So there is no easy isomer. And if you will just hydrogenate this particular product, which is having an alkyne group, and you know that in presence of hydrogen, it would turn to a double bonded system. And that is, I'm not writing the whole part. So this is your Z alkene. Z alkene symbolizes the cis isomer, if you can understand it better way. So what we understood from this part, I'll just give you a little brief, that if you have a choice of ene and ene and ene, so depending on the catalyst it will undergo. So in presence of your metal carbene, it would prefer ene and ene metathesis. And then when we have metal carbine, it would go ine and ine. metathesis. I hope this is clear. I'll just explain it one more time. So what we were having in the same molecule, we were having two alkenes which would undergo metathesis. Similarly, this one ene could have combined with the alkyne to give you another product. But in presence of our first catalyst, which is a metal carbene, it preferred to form a metathesis, which is combination of two different alkenes, giving you a five-membered ring and having an open alkyne group. Now at this step, if I'm adding a metal carbide, it would take 2 units of this particular metal carbide to give you a long chain, another alkyne, which is your product. And on hydrogenation, it would lead to formation of an alkene. So in this type of reaction, the highlighting points are, so here we didn't find any E or Z isomer in alkyne metathesis because it would not be having any choice of it. It is just a linear chain. Second, we found that after we have formed a alkyne, new alkyne after the metathesis that can be further reduced to only Z alkene. So here we are getting the selectivity. Selectivity has been increased because it would readily be giving you one type of alkenes, which was not possible when we were doing with the alkene metathesis. And this method finds wide variety of applications because here we are directing it towards in a particular direction, and also it is giving us a particular selectivity. It is not giving us any isomers over there, and it is forming one product as a major product, which enhances the productivity and the yield of the desired product. So this is with respect to the enine alkyne enine metathesis, depending on the which catalyst we are going to incorporate in our systems. So yeah, this is the part that we wanted to explain. So with that, our live session discussion regarding the different topics is completed. So I hope you have understood it. We'll just take a revision of what we have said so far, summary. No, we still have 40 minutes in hand. After the summary, I would be explaining some assignment problems, and you will be able to understand it more properly how you have to apply these concepts in solving the questions. So, summary of week 6 live session that we are going to talk about. So, the first thing that we started was your first part was your ring closing metathesis, where we saw that depend if one example was there, if groups are different, then the products would be different. If we have many choices, so that you can see which product would be formed in presence of which uh, with substituent. Secondly, we talked about the asymmetric ring closing metathesis, where in asymmetric we got to know that uh, one such example where five-membered ring was preferred over the three-membered ring because of the strain. Also, we saw that macrocyclic macrocyclic product formation was the was favorable over any other membered ring. Followed by we had the tandem cross metathesis, which talks about the dimer is to trimer ratio. And we saw that more concentration of substrate would lead to more trimer formation, and it is the substrate concentration dependent. Then our third point was ring opening, ring closing metathesis, which is very, very important, where it would first undergo the ring opening of your strained ring and then followed by the ring closing to give you a more stable ring formation. Say for example, if I have a possibility of 6-membered ring to be formed over the 5-membered ring, the stability is more. Therefore, it would prefer to form a 6-membered ring. If 6-membered ring is forming in my product over the uh, north Bodney, that means that 7-membered bridged kind of system, I would prefer to form a 6-membered ring. But how it forms, first step would be your ring opening and second step would be your ring closing. And the last part of our discussion was the uh, ring, sorry, the last part that we discussed was alkyne metathesis, which is more or less similar to our uh, alkene, where we need to understand if we, in alkyne metathesis, these are the possibilities that if we have different kinds of group, it would also undergo the cross metathesis as the way it does with alkene. The point is like it can undergo alkyne alkyne or ene kind of systems. Then we saw that it works. RCM ring closing metathesis of alkynes works under high dilutions, and it would always lead to a cycloalkyne formation and a open alkyne, where we saw this kind of example. It is closing here, making a cyclo product, and it is giving you an open chain volatile alkyne. Now, when we have a choice of two alkenes and one alkyne, firstly, in presence of metal carbene, it would tend to give you a metathesis, alkene metathesis product by closing the ring. And then 2 units of this particular ion systems, they would extend the chain to give you a self metathesis metal alkyne product. Then after hydrogenation, this alkyne would reduce to form an alkene. And the highlighting points were that we don't see any E or Z isomer when we are talking about alkyne. E and Z isomer are only possible for alkenes. Then the alkyne which has been formed as a product that can be easily reduced to alkenes, and that alkenes is having a selectivity only of Z alkene formation. And this method can be used to make a lot of products in natural product synthesis. So I hope this is clear to all. If there is any question, please put your question in the chat box. I'll be happy to make you understand it even better way, or else we can start with the assignment problems. Is there any question? If not, then please rejoin the same link as it is going to end this particular meeting for assignment solution.